Everyone, I'm Zihao from Tsinghua University. I will introduce our recent work BiCord, which builds bidirectional coordination among coexisting wireless devices. In recent years, the Internet of Things has grown rapidly. Various types of technologies are developed to fulfill different application requirements. An increasing number of wireless devices are deployed in more and more practical scenarios. For example, in a smart home scenario, we use Wi-Fi devices to connect to Internet and lots of low-power sensing nodes to collect information. These wireless devices are crowding the ISM band in the 2.4 GHz, causing severe cross-technology interference. In real-world scenarios, due to the power asymmetries of different wireless technologies, devices may not hear each other's transmissions and interfere the ongoing transmission. For example, the transmission power of Wi-Fi is much higher than Zigbee, so Wi-Fi devices are usually unable to sense surrounding Zigbee traffic and may corrupt the ongoing Zigbee transmissions. As a result, Zigbee nodes are highly vulnerable to the interference and cannot obtain enough channel resources. To handle the interference, traditional approach let low-power devices measure, assess, and predict the availability of the channel. For example, Zigbee nodes locally detect the traffic pattern of Wi-Fi traffic and then predict the occurrence of white spaces which are free of Wi-Fi traffic. This mechanism performed poorly with high traffic dynamics, as Zigbee nodes cannot obtain an accurate traffic pattern of nearby Wi-Fi devices. They still suffer from collision and the lack of channel resources. Recent approaches use cross-technology communication techniques for channel coordination. For example, in ECC, Wi-Fi devices broadcast a control packet to notify nearby Zigbee nodes about an upcoming white space, so that they may use it for transmissions. However, without knowing the requirements of the surrounding Zigbee nodes, a Wi-Fi device can only blindly allocate the channel for Zigbee, which leads to an ineffective channel allocation. Moreover, Zigbee nodes can only wait for notifications and suffer from a high transmission delay. To summarize, existing approaches cannot solve the interference. We need a scheme to improve the performance of low-power nodes and to increase the channel utilization. To achieve this, we propose bidirectional coordination, which enables proactive request of channel resources and on-demand channel allocation. In the first part, we describe the main challenge. Due to the power asymmetries, it is difficult for Zigbee nodes to interact with Wi-Fi devices and let them know about their needs. Moreover, existing cross-technology communication techniques from Zigbee to Wi-Fi are unsuitable to build a channel coordination scheme. Recent methods like Zigfi enable Zigbee to transfer information to Wi-Fi devices, but they need a tight synchronization. The process would incur long delays of about 110 milliseconds. Compared to a typical Zigbee transmission of about 30 milliseconds, the benefits of the coordination scheme would be neutralized. The observation here is that Zigbee nodes only need a signal to inform the Wi-Fi devices of their need. In the next part, we introduce the design of BiCord. This figure shows the design overview of BiCord. It mainly contains two modules. First, in the cross-technology signaling module, after Zigbee nodes have corrupted or lost data and detect cross-technology interference, they directly signal Wi-Fi devices the need to access the channel. This module then makes Wi-Fi devices allocate the channel to Zigbee. Second, the adaptive white space allocation module makes Wi-Fi devices provide on-demand channel allocation for Zigbee nodes. In this module, the Wi-Fi devices learn the traffic pattern of Zigbee transmission and adapt the length of white space so as to increase the channel utilization. This figure shows the workflow of cross-technology signaling module. When a Zigbee node finds corrupted or lost data due to Wi-Fi transmission, it transmits control packet with a higher power to inform the Wi-Fi device that it needs channel resources. Wi-Fi then obtains this signal by CSI analysis and issues a white space for Zigbee transmission. The Zigbee sender receives acknowledgement of control packets, infers that Wi-Fi stops transmission, and then utilizes the white space for data transfer. We also want to note that to make Wi-Fi side quickly receive the signal from Zigbee side, BiCord does not need Wi-Fi device to fully synchronize it to Zigbee. Instead, the Wi-Fi device detects the existence of Zigbee transmission based on the CSI values of packets and then issues the white space. To increase the channel utilization, BiCord uses the adaptive white space allocation module to determine the length of the white space. The traffic pattern of Zigbee is relatively stable, so BiCord uses a strategy to make Wi-Fi devices estimate the length of Zigbee transmission. The strategy involves two phases. In the learning phase, the Wi-Fi device starts with a white space shorter than Zigbee transmission. To complete one transmission, the Zigbee node needs to signal Wi-Fi multiple times. During this round of signaling, the Wi-Fi device is able to estimate Zigbee's traffic pattern. After that, Wi-Fi device adapts the length of the white space based on the estimation. In the second phase, the Wi-Fi devices allocate enough white space for Zigbee nodes to finish the transmission. This way, BiCord improves the performance of Zigbee nodes and increases the channel utilization. The last part is the system evaluation. We evaluate BiCord in an office environment using commercial Wi-Fi devices and Zigbee nodes. The deployment of these devices are shown in the right figure. We first evaluate the two modules of BiCord. In the cross-technology signaling module, the detection of Zigbee signal at Wi-Fi side achieves the precision and recall of about 90%. As for adaptive white space allocation module, the Wi-Fi device uses 5 iterations and leaves the white space of about 70 milliseconds, sufficient to contain the Zigbee transmission of 62 milliseconds. We also compare the performance of BiCord to the state-of-the-art approach ECC. In terms of channel utilization, BiCord especially outperforms ECC with infrequent Zigbee traffic and achieves a 50% higher channel utilization. In terms of delay, BiCord outperforms ECC in average by 84%, and the average Zigbee delay is well below 30 milliseconds. In conclusion, we analyze the need of the bidirectional channel coordination, propose BiCord, a scheme including two modules, and then implement and evaluate it, demonstrating its effectiveness. We also plan to extend BiCord to other coexistence scenarios. For example, using cross-technology communication techniques from Zigbee to Bluetooth, BiCord is able to coordinate coexisting Zigbee and Bluetooth networks. Thank you. Please visit our website for more details.